So, why do we use differential amplifiers to measure voltages on the skin's surface? Hang on a second, why are we measuring voltages on the skin surface anyway? Well, cleverly, scientists have been doing it for years to measure brain, heart, muscle and nerve action since Willem Einthoven made it popular and won a Nobel Prize for doing the first ECG in 1924. So how does it work? Well, you place electrodes on the surface of the body after you've washed away the mud and dead skin, then measure the potential difference between the different parts. For an electrocardiogram, or ECG, there are 10 leads, 1 placed on each limb and 6 on the chest, to see the electrical changes in the heart during a heartbeat. For an electroencephalogram, we place 22 or more electrodes on the scalp to measure the electrical potentials of the brain. These electrodes measure the potential difference between each area, but the problem is that the potential differences are very small, while the noise in the input is high as well, making it hard to see the signal. This is where the differential amplifier comes in. It reduces the noise and increases the signal, improving the signal-to-noise ratio. But why can't a normal amplifier do that? A normal amplifier has 2 leads, an active and a ground lead, and whatever signal goes into the active lead is amplified. Normal amplifiers are no good for surface electrodes because the signal is too small and the noise is so big. But a differential amplifier has 3 leads, and instead of amplifying the signal, it compares the active signal with the reference signal and amplifies the difference. This gets rid of the noise because it is the same in both wires. Because the voltages measured are so small, at around 50 microvolts, the differential amplifiers increase the signal normally by 10,000 times, a differential gain of 10,000. But do you remember when I said that there is no noise in a differential amplifier because there's 3 leads and the noise doesn't get amplified because it's the same in each lead? Well, that's not true. Some noise that is common to the 2 electrodes gets through and even amplified. It's called the common mode gain or common signal gain. An ideal differential amplifier has a high differential gain and a low common mode gain. If we want to describe how good a differential amplifier is, then we combine the 2 figures into a common mode rejection ratio, or common. So differential amplifiers have 3 leads, but only the reference and active receive a signal. The active electrode is placed close to the area being measured, and the reference is placed nearby. Any noise should be the same in both leads, and therefore not be amplified. The signal should enter the active electrode, much more than the reference electrode, and then be amplified drastically, leaving a beautiful noiseless signal. But problems occur when the reference and active electrodes are too close together. Their signals will be too similar to differentiate. Also, there's a problem in noisy wards where background noise is picked up by both electrodes and amplified. To stop this, you can use a shield to block the noise. And that's all I've got to say on differential amplifiers. Thank you very much. That was Benjamin Hardy.